Hello, my name is Harry Kim, and I'm CPO at XCENA. And it's good to know there is needs for hardware acceleration, and also good to know about Velox memory management. So XCENA is a family startup bringing CXL to the data processing world. We are working on developing hardware and software solutions to accelerate Velox with CXL computational memory. So data is rapidly increasing, but we are reaching the limit of how small we can make a DRAM cell. So as a result, memory capacity, bandwidth, and performance are no longer doubling like they used to. So while data is exploding, we need better ways to process them. We often run into out of memory kills or suffer from performance drops due to disk spills. And in many cases, workloads vary so much. There are peaks, and that you need heavy tuning, like Meng said, or over provisioning just to keep up. So, and scaling out with more servers works, but bring with some more complexity and often diminishing returns. So how can we tackle this? What if a single node with dense memory and compute could replace an entire cluster of 10? This is where CXL comes in. CXL is a protocol built on PCI Express that lets you plug in your memory as the same way you plug in your GPU card. And CXL memory looks like just regular memory with additional latency due to protocol overhead. And it gives memory pooling or sharing with through switches. But to us, the most exciting part is that also it supports cache coherence, which makes it a foundation for heterogeneous computing, not just memory. So at XCENA, we are building computational memory on top of CXL. That means memory can do computation, what's called near memory compute or near data processing. Our journey starts with building a high quality, high performance CXL DRAM expansion for the baseline, and then we extend it to use SSDs to create a much larger and more affordable memory tier. So we call what we call infinite memory. On top of that, we integrate thousands of RISC-V cores into the memory controller itself, and then build the software stack to drive them. To make this more useful, we also provide a data processing library which connects with a data processing engine like Velox. So our goal is simple: more memory, less data movement, get better TCO. Now, so CXL memory offers more capacity and extra bandwidth, but there's a little bit slower than main memory when it comes to latency. So when you put a lot of data into a CXL memory and access it through a CPU load store, it can hurt performance and waste power. That's why our approach is to offload some operators like scan, filter, or basic math to the memory itself. So the CPU doesn't have to touch that data at all. This reduces memory traffic and frees up CPU cycle, resolves cache lines, so CPU can focus on what it needs to do. We are building a custom SoC that combines CXL with a many core architecture. It has over thousands of RISC-V cores supported by a high performance cache hierarchy and memory systems. This is designed for large scale workloads and parallel processing like vector database, Spark, Presto, or even graph analytics and DNA analysis. Yeah. The product comes as a adding card type like a GPU. We are going to use just RDIMM slot. It might have different form factor at production. You can plug it into a standard GPU slot, and it gives you up to 2 terabytes of memory. We're launching this card by end of this year. We can use this card to build a memory pool with acceleration capabilities. Even more interesting, the card includes a PCI root port, so you can directly attach SSDs to it. This setup gives you tens of terabytes of memory per card, cached by terabytes of DRAM. And this allows a single chassis to scale up to petabytes of memory. So let me give you some more detail. XCENA controller includes additional PCI Express root port, so we can connect SSD directly. So if necessary, multiple SSDs can be attached through a switch, and RAID setup can be used to enhance SSD reliability. Inside the SLC, we run a paging algorithm that automatically caches SSD pages into DRAM and handles all the mappings and address translations. So you don't need to reformat data and invoke IO thread for disk spills. You just write to memory, and XCENA handles the rest. Terabytes of DRAM tracks your active working set, and behind that, SSD give you tens of terabytes of extra memory. Let's talk about acceleration. When you use accelerators, they normally require explicit data copies. You need move data in with, let's say, CUDA main copy and out again when you are done. CXL is different. It's a part of CPU system memory space. When CPU stores data, it flows through the cache hierarchies and lands in CXL memory, so no memory copy needed. So this is huge. It means our CXL device can process data in place without wasting time or bandwidth on large data copies. But there are challenges. Applications run on the user virtual address, and CXL memory sits in the physical address space of the host. So for shared access, device must also support virtual addressing. And we must isolate each process's memory for security and correctness. That's why our solution supports cache coherence and virtual addressing, so we can offload complex or pointer-rich data structures without transforming them. This enables fine-grained offloading and lets the CPU and CXL device work together. Each can do what they are best at. And all of this works with our SSD-backed memory transparently. And of course, to use all of these hardwares, we need a strong software stack, like CUDA for GPU. Our SDK includes a compiler, libraries, simulators, and more. And we offer 3 layers of software abstraction, which I'll walk through now. So we started with a low-level device API to control threads directly, but as you might expect, it's complicated and requires deep hardware understandings. So not very productive for everyday development, and it's doable though. We don't recommend users to do at this level is to complex. So we created PXL, which is Parallel Acceleration Library. It's a runtime and API layer inspired by MapReduce. Now you can write programs with more familiar constructs like job or map objects. We are also working on shuffle side for reduction and planning to extend for graph workloads and communication primitives. PXL is available for internal and external development who want to write their custom kernels. So before we move on to the next third layer, let's take a quick look at how CXL hardware and software are structured. CXL memory could be accessed by CPU using standard load store instructions, just like any other memories. It's just a memory. So, but with XCENA computation, things get more interesting. You can write programs using PXL to process data in place where it lives. This means the host CPU doesn't need to fetch the data and process it directly. That saves CPU cycles and avoid unnecessary case pollution, and that improves a lot for the efficiency to data processing. That said, parallel programming is still not easy. How many people feels happy with writing CUDA code directly? It's quite hard. Most developers prefer just using higher level frameworks like PyTorch. So that's why we are building another third layer like XFLARE designed to process OLED queries based on open formats such as substrates or and Apache Arrow. So XFLARE works as a backend for Velox, enabling query offloading and acceleration to the device. It's a plugin like a web project for GPU. We can use Presto or Spark through Gluten as a front end. We also provide a data-specific API called XVector, which is integrated with a Vice library for vector search queries. So here's a basic concept how XFLARE works. XFLARE integrates Velox through a driver adapter interface. It's similar with NVIDIA cuDF, and we want to keep minimal modifications in Velox. So it takes the Velox plan and transforms it to a local kernel that fits our hardware model, and we optimize it and chooses the best execution plan for each operators. So if there is high parallelism, then the operator will be executed on the device side. If strong single thread performance is needed, then the operator will be executed on the CPU. In some cases, it just falls back to native Velox. In this context, we want to work closely with Velox community to explore efficient use of CXL memory and to contribute to the Velox. So, call to action. CXL brings opportunities as well as challenges. Integrating Spark, Gluten, and Velox will not be easy. Memory management from different kind of software stacks are also challenging, and it's very important topic. We want to participate and invite the community to work together in reimagining the data processing infrastructure with CXL. And when you have time, please visit our website, xcena.com/SDK, and you get some early hands-on experience with CXL computational memory. Yep. I'm super excited to join and being a part of this new journey of CXL and reshaping data processing infrastructures. And I think that's it for today. Thanks for your time.